In the beginning of the 1900s, scientists were facing a conceptual crisis. Everyday phenomena had successfully been understood, but our understanding deviated when dealing with extremely high speeds and small scales. New theories had to be built over old ones, or old ones had to be tossed out altogether. One phenomenon that baffled scientists was the photoelectric effect. When light hits metallic objects, electrons would rebound from the metal surface. But scientists' theories could not explain how this worked. At the time, the big craze was that light behaved as a wave, though few scientists wrote these waves differently, Albert Einstein in particular. Einstein theorized that light consisted of quanta, or packets of energy, or photons, basically behaving like a particle, whose energy was dependent on the frequency. Wave theorists expected more electrons to be bumped off, as it seemed that more energy was put into the intensity of the light as it went brighter and brighter. But it was evident that intensity wasn't a significant factor to bringing the electron out of its hole. Einstein regarded light as individual packets, and to disturb electrons from the metal surface, they each held yummy energy individually. Each yummy-filled treat managed to get an electron out successfully. Each packet consists of a specific amount of energy that is dependent on the frequency. So the more frequency this light has, the more energy, and will easily carry an electron off. This quantized view of light was based off a hypothesis by the scientist Max Planck, who characterized the energy to be in relation with the frequency, E equals hf, a symbolic equation in physics, and you can understand it once you realize it's just a linear equation. This gap before the graph starts are frequencies too low of energy to set an electron off the specific metal. This includes the visible light spectrum, and below, in the bracketed, is the energy transferred to the electron before it escapes the metal surface, W. Also note that as the atomic number of the specific metal is higher, it takes more energy to remove its electrons, and therefore higher frequencies of light are required. Thanks to Einstein, wave theorists were scrambling to explain it their way, but the quantum theory had prevailed to this day in explaining the photoelectric effect and other small-scale phenomena like it. Far from the photoelectric effect, new properties of other subatomic particles are well known now. For example, uncertainty, wave-particle duality, orbital theory explaining the subtleties in chemistry, cats, and particle interactions. If it weren't for Einstein's application of Planck's quantum hypothesis to set us straight, who knows how far we'd go with our waves. Probably sleeping with the fishes.